Well, good afternoon, everyone. So today we're going to transition into a topic that, to me, is sort of the reward for having slugged through all the low-level stuff you've done up to this point, to be able to really understand and become adept at programming network software. There's a lot to networking that we're not going to cover, but at least to have some familiarity with it. So I know that a lot of you are sort of in the midst of trying to figure out how to make malloc run and make it run fast. And so this topic is really more pointing toward the future, but it's very relevant to the final lab you'll do for the course. And so we're starting to get ready for that. So, like I said, this course is not really a full course in networking. There's many other courses at the university that are. And so what we're going to try and do is give you just a little flavor of it, and particularly, as everything in the course, a programmer's perspective. So how you as a software developer would make use of the C-level APIs that are relevant to network programming. And why isn't this working? Okay. So the idea behind most networking systems is what's called the client-server model. And the idea is that there's a service out there that you want access to, and you as a customer or a client are making a request to that server. So an example would be when you order something on Amazon. Amazon has a bunch of servers, and you go to your web browser and it contacts the Amazon web server, and you make transactions. You request something, you provide information, and it gives you back pretty pictures of things you might want to buy. It acknowledges your credit card transactions. Those are all very classic client-server types of interactions. You as the client, Amazon as the server. Another interesting example is a telephone. So if you think about it, a telephone is both a client and a server, in that when I'm placing a call to somebody else, I'm the client and that person's phone is the server, right? It's sitting there waiting for calls to come in, and when that call comes in, it makes a connection. We talk over the phone, and then I hang up. Either side hangs up. So there's a lot of instances out there of some variation of client and server, and it's a much richer idea in that you can often switch back and forth the roles of those two parties. But it's a pretty universal and ubiquitous way of thinking about how to set up a network system. So in general then, the idea is that there's this thing's not working. The client is making some request to the server. The server does something locally to deal with it. It gets information. It retrieves from its database the things you might want to buy. And then it sends back information, say a nicely formatted web page with all kinds of shopping suggestions. And then the client decides what to do next. So from a hardware perspective, the interface to between the network and your computer is called the NIC, or Network Interface Card, even though it's not always on a card. And we really won't talk about hardware at all, but what's most interesting from it is that it looks to your computer like an I/O device. And in fact, the Unix API for dealing with networks makes it look like a file. So in particular, just as a disk sits off of a bus and you write data to a disk or you read it from a disk, similarly the network sits off of a similar bus, and when you want to send a message, you actually do it by writing to a sort of virtual file that's called the network. And if you want, when you're receiving data, you do it by reading. And so just as several weeks ago I gave the lecture on I/O, it turns out that that's extremely relevant to network programming. And that's the basic model that was created by the early developers of the sort of standard Unix. And now that's carried over not just to Unix, but it's the same model for Windows and other operating systems. So, and now let's just talk a little about what computer networking means. The idea of a network is it's a collection of systems that are referred to as hosts that are able to communicate with each other over some kind of communication fabric, let's call it, communication system. And they're sort of partitioned into mostly referred to as LANs or local area networks that you establish within a small region, and then a wide area network, which would be over something the size of a city or perhaps more. And over an enterprise such as CMU, it's a very complex set of, for example, there's wireless base stations that right in this room that you're interacting with when you're using a wireless system or your phone. And then there's a whole networking infrastructure within the university that then goes to some commercial providers, AT&T in particular, that give it access to the commercial internet. And then there's another set of network connections hosted by the supercomputing center that give you access to what's called Internet 2, which is the resource that's used for communicating among universities. So underneath, when you're doing your networking stuff, there's this amazingly complex combination of things going on. The idea of an internet refers to the general idea of a network of networks. Taking, for example, the local area network that this base station provides and connecting it up to other networks on campus and across the world. And when we refer to the capital I internet, that refers to the one instance, the most significant instance of an internet. So lowercase I means the sort of general idea of creating a network of networks. Uppercase I is the specific example that we all know and use all the time that's organized by a certain set of principles that uses a particular set of protocols and so forth. And of course, we tend to just talk the internet, and most people know that what that really implies is the sort of existing network structure that there is. And that's good enough for the purpose of this course. We're not going to talk much about other possible designs one might have for a network. So most of the low-level networking is supported by something called Ethernet. And the term Ethernet actually has evolved tremendously over time so that it's almost more like a brand name than it is a specific technology. And the version you're familiar with, the wired version of it, you have a wire to some sort of a box like that you plug your Ethernet jacks into. And historically, those were called hubs. And the idea of a hub was it was just a repeater that whatever came into it from one computer, it would broadcast to all the connected machines. And so you only want to do this for maybe a dozen or so machines. It's like a party line. They're all hearing what everybody else is saying. And in fact, the original first version of the Ethernet did that by everyone interacting over a single cable carrying essentially radio signals. And similarly, when you're in this room using a wireless internet is sort of like a hub in that all the packets that you're sending all across the room, they're all sort of making use of the same radio frequencies, the same communication channel, and there's a protocol for how they detect when two messages get sent at the same time and therefore interfere with each other. So that can only sort of scale up to maybe at most 100 different hosts communicating because they're all sharing a single communication channel. Now in the wired world, what's evolved is usually when you buy a box or you get one from your cable company with all those ports in it, it's actually called a router or sometimes a switch in that it doesn't broadcast to everyone. It selectively tries to guess, is this particular message bound for this particular host, and only send to that one. And as you know, you can take these and wire up, I think about up to 6 levels deep in hops, and basically create a network of wired connections, and they'll all get from one to the other somehow. And then after that, it gets more complicated. You can add more sophisticated types of switching on top of it. But so the general idea of even an Ethernet is actually a fairly complex thing. But at some sort of conceptual level, we can just think of it as a bunch of hosts that can talk directly to one another. And then an internet then refers to the idea of taking those local area networks and connecting them together via routers. And routers obey a particular protocol based on the address that you're trying to send data to. And, and so what you end up with conceptually is a whole bunch of hosts spread potentially all across the world, and then some magical system of routers that will get a message from one place to the other based on a mode of addressing where there's some known address of the host that you're trying to send to, and it will hop through multiple routers to get from one place to the other. And that's true whether it's on campus or whether it's hopping all the way around the world. And so, again, there's this huge body of information and knowledge about how that routing works and how it's reliable and all that. But we're going to just assume that somebody else has figured that out. And our job as programmers is just to be able to communicate from one host to another. And so how could you design a system where all these diverse systems made by computers, made by different manufacturers, operating under different countries with different telecommunications bodies, governing bodies, and so forth, how can they all work with each other? And the requirement is you have to have a protocol. You have to have some common set of conventions for what messages look like, how they get sent, what happens if one of them doesn't make it, how do you recover from that, and so forth. And so what does a protocol include? Well, it has to include some way of naming things so that if I want to send to some host, I have some way of designating who that host is, and then there's the routing system has to have some reliable way of getting my data to that named host. And that's the delivery mechanism. And that's usually done in one of the things that we now accept as universal, but it really wasn't when it first came out, was idea of you take all your data and you divide it into packets, and packets are typically about 1,000 to 2,000 bytes. And so if you have a longer message, it chops it up into individual packets and sends it across. And all the communication occurs at a packet level. That's different than the historic phone system was a connection-based system, meaning that if I was calling somebody, there was a dedicated set of wires maintained by the phone company that would be reserved and locked down for our own use during the entire duration of that phone call. So to get then from one host, say A, to B, what happens is we want to send a packet. And that packet will contain some amount of data. And the idea of packet communication then is you put little headers on that contain sort of routing information, the equivalent of what you'd see on the front of an envelope of a letter, perhaps. And so, and at different points in the way, they'll have different numbers of headers and different protocols or formats for what those headers look like. So in particular, within, I want to send a message, and I'll do that, and then the software that runs on my machine that handles this will put a header in front of that that describes the internet routing, and then it will tack a header in front of that that talks about the local area network routing that gets used. And that's what's referred to as the PH, the packet header for the Internet Protocol, and FH1, the frame header for this particular message being sent within this local network. And then the network interface card, or the adapter here, is then responsible for putting that out over this local communication capability, and then that gets received at the other end by the network adapter at the receiver's direction. It will put its own frame header on it to pass it in, and that then gets stripped off so that all host B sees is the data that gets sent. But this idea of putting headers in front and at times sort of what they call encapsulation, that I'll take this big packet and I'll just tack some more information on top to the front of it, header information, and I'll send through the rest of it just as a set of bytes. So the internet that we know and love, the capital I internet, then has a particular set of protocols that are, you've probably heard the terms. One is called the IP, the Internet Protocol, which is the one that defines ideas about how do you name hosts on the internet, and how do you send packets. And they're referred to sometimes as datagrams, meaning that a packet is just a single entity that gets sent from point A to point B. And the underlying IP doesn't guarantee delivery. So it's based on what they call best effort communication, meaning that at each step along the way, if, for example, things are good, then it will just send this packet along. If there's too much congestion, there's been somebody's turned on their microwave oven and it's set up some radio frequency interference, then at the IP level it just drops that packet and says, whoops, I screwed up, sorry. It doesn't even say sorry, it just does it silently. And then you can, as a programmer, make use of that very low level. So normally as a programmer, you don't really want to program at that level because you'll send packets and they won't get there. But you can if you want to, and it's called UDP protocol. It's just a small software layer over IP. And there's some applications that you'll see, for example, in the computer game world where you want to send information really fast, and if some information gets dropped, it's not a big deal, that people actually program at that level. We won't really talk about that. The more common protocol that gets used and carries 99% of internet traffic is what's called TCP, or Transmission Control Protocol. And that provides a reliable, the equivalent of a telephone connection, that I can reliably send data from point A to point B, as many bytes as I like. It's guaranteed delivery. It's sometimes fast and it's sometimes not, but it's there. And it's built on top of the IP, or this datagram, meaning that it has to take whatever you're sending and slice it up into these single packets. If one of them doesn't get sent, it will resend it until it gets there. They have to deal with the fact that packets can travel different paths and one can get ahead of the other in transmission, and so it has to reorder them in the correct sequence. And so there's a lot of stuff under it, but we'll just assume that it kind of works. And so you can just think about it as I have a stream connection. I can send from A to B, and B can send a stream of data back to me, and we're all happy. And so that's the version that looks like file I/O. I just keep writing to a file, and it's sending packets over the network to the other end, and then the other side can be sending stuff to me, and I'm just reading it, and I'm just reading bytes of data, not worrying about how that got broken up into individual packets. And so that's referred to as the sockets interface. You'll hear the term socket programming, and that's exactly what we're talking about. And so from a sort of software system, then, software hardware system, then, The client and the server are both implemented as application programs at their respective endpoints on their hosts. And they make use of software libraries that run at some combination of the user level and at the kernel level, and therefore have access to direct resources. And so I, as a programmer, an application programmer, then make use of this software API that lets me do socket programming. And it's based on, directly supports TCP/IP. So first of all, we're going to talk most of the time about what's called IPv4, version 4, which is the one that's been running for since the 1980s, I think, early 1980s, and is the standard. And we'll only mention very briefly the idea of what's called IPv6, which is sort of a next generation version. So the idea of IPv4, and this is now we're talking about IP, and this is true of TCP as well, is that an address is actually just 32 bits. But it's usually expressed in what they call dotted decimal form. And you've seen these addresses before, that it's 4 decimal numbers, and they can only range between 0 and 255, because each one of them is a single byte's worth of information. So we're used to writing things in hex now in this course, but we're going to write it as each byte is written as a decimal digit. And they're actually passed and stored in what's called network byte order, which is big Endian byte order. And so we have to worry about the whole big Endian versus little Endian thing when we're doing network programming. And you can actually learn a lot. There's a whole levels of how the different bytes mean. But for example, any IP address that starts with 128.2 is at CMU. I think, and then, and so essentially CMU owns that part of the IP address space, which if you think about, that's approximately 2 to the 64th, 2 to the, no, not 2 to the 64th, 2 to the 16th different IP addresses available for use by campus. And as I mentioned, there's a newer version called IPv6 that gives you 128-bit addresses. You can imagine actually that if you think about how many nodes are there in the internet, if a 4-byte address is only 2 to the 32, so that's 4 billion. And I don't know about you, but I have a lot of different things that use IP. I have a phone, I have 2 laptops, I have a couple desktops. So if every one of us used multiple IP addresses, then actually the world would be out of them, right? There's 7 billion people in the world, not all of whom have access to the internet, but a large fraction of them do. And so there's a whole kind of crazy way of dealing with the multitude of possible IP addresses. So the obvious thing would be, well, let's just allocate a lot more addresses and let's just skip 64 bits and go right to 128. And that's the idea behind IPv6. But quite honestly, this has been one of those technologies that's been out there for over 15 years and still has a very low level of adoption. So it's still a future technology. People have basically figured out all these crazy schemes to make use of just stick within the 4-byte limit. Okay, so let's start talking the sort of programmer perspective on this. And this is one area where you'll wish you weren't programming in C, but you are. So there's a lot of really crufty stuff, and it was all developed, most of these software protocols were conceived before C even was what it is today. So like the Kernighan and Ritchie book you have is called the second edition, and it's based on what was called ANSI C or ISO C. But these all date before that. They date back to the original Kernighan and Ritchie. So for example, void star did not exist in that era. And so you use char star as a generic pointer. And so there's just a lot of stuff in this programming interface where you go, wow, that is really crufty. And the truth is, yes, you're right. So in particular, there's a lot of different structs that are defined. And one of them is called an in-adder, which means internet address. And it's just defined to be a 32-bit unsigned number. And in general, as I mentioned, the so-called network byte order, whoever designed the original protocols was a fan of big Endian addressing. And so that's what it is, even though actually most of the machines that are out there in this world are little Endian. And so there's a set of standard library functions that you use to convert between network order and host order. And the idea of it is, now if I run my software on a little Endian or a big Endian machine, these functions will do the right thing. So if I just use these standard libraries, then I don't have to worry about porting it every time I change the word ordering of the machine. One of the things you'll notice here is there is no function to convert 64-bit data between network order and host order. So I don't know what people do. When I do it, I just write my own functions to do it. Or I don't, because I know my other end is a little Endian machine. So anyways, these are already some functions you'll start seeing for that look like network conversion software. And as I mentioned, the addresses are written in dotted decimal form, and it's also big Endian. So if I were to write in hex, 128 is, of course, 80, so that's the most significant byte of the IP address. And then there's a set of functions, API calls you can use to convert between this dotted decimal format and the actual just a 32-bit unsigned int. And actually, it used to be, you might see some older presentations where they use different names for this, but the most recent version API calls this the presentation version, the dotted decimal, they refer to it as a presentation. And you can look up and it's in the book too, what the calls to these look like. But you probably don't, or very seldom, when you're thinking about, I want to go to Google, you don't think about what its IP address is. You just go to www.google.com. And for everything you do, you refer to it by this, what are called internet domain names, which is a hierarchical naming system where, as you know, there's .edu is for educational institutions, .com is for commercial, .net is general networking. Many countries have their own suffix, so .de is for Germany and so forth. And so those are called the first level domain names, and then there's a hierarchical naming structure under that. And there's actually an interesting question of, okay, how do I then map from those hierarchical names, those domain names, into this dotted decimal or the 32-bit IP address? And the job of that is by a very large distributed system called the DNS, the domain name system, where the only sort of centrally managed part of it is at the top level. So for each of these first level domain names, there's a collection, a very large collection of machines that keep track of all the IP addresses that map to one of those first level domain names. And then, for example, CMU maintains its own naming authority. So anything that says something.cmu.edu, there's local DNS servers within CMU that are picking apart, okay, where should, if I say cs.cmu.edu, what would be the the IP address for that. And it's actually pretty interesting how this is managed because it's totally decentralized. There's a whole set of protocols that govern how naming is done. But conceptually, we can think of it as just this big database that gives me a mapping where I can give a domain name and it will get back to me one or more IP addresses. I can give an IP address and it will come back with one or more domain names. And so there's actually an application you can run on most machines called NSLOOKUP, and there's another one called DIG that you can use to find, basically probe the DNS and find in either direction. You can look at given a domain name, you can find its IP address. Given an IP address, you can find its domain name. And I'll show you some code that, just as an example of how you do the programming. I'll just show that momentarily, called hostname. So just some examples. You know, if I look up some address, like the website for the computer science, School of Computer Science, using NSLOOKUP, it comes back. Can people see this okay? Do you want it bigger? It's okay. So this is what NSF looks like. And this stuff here just tells you, you know, where was the actual directory entry which DNS server actually gave this information back. And it says that www.cs.cmu is actually a synonym for a weirder one called web-lb.serve.cs.cmu.edu. And its IP address is 128.2, like you'd expect, 217.13. And of course, that works not just at CMU, but I can, you know, go ask what Stanford is up to, and it will come back, and its IP address is something 171.64, and that's been managed by that. And you'll see again, I asked for www.cs.stanford.edu. It said, well, the real name of that is cs.stanford.edu. And this actually is a point that the mapping between domain names and internet addresses is not one-to-one. You can have multiple domain names that refer to the same internet address, but you can also have multiple internet addresses. Excuse me. That's weird. So like twitter.com, when I ask for it, it comes back with 4 different addresses. And if I do the exact same thing again, yeah, you see it came back with the same, no, not even the same addresses. It came back, for example, here, the one that ends with .6, that wasn't in that first list. So it came back with a slightly different set of addresses and a somewhat different order. And the idea of that is that it actually has multiple servers. So when I send to twitter.com or Google or any of these major servers, there's not just one place in the internet that's handling everybody's Google traffic. There's thousands of places spread around the world. And the way they get you there is by playing tricks with the DNS. That Google is constantly sending updates to it maintains its own DNS servers. So it's constantly changing them. And it will actually give you different addresses depending on where in the world you're located as well, to try and provide a server that's sort of reasonably close to you geographically. So there's just all kinds of tricks that happen through DNS that is part of the way they can sort of manage this huge set of addresses. And then there's some other domain names that don't have any IP address. That they're somewhere in the hierarchy, that hierarchical naming system, but they're not actually referring to a particular host. So it's a multi mapping. And the API sort of reflects that. So this is just going what I told you. There's sometimes one-to-one, sometimes many domain names refer to the same address. Sometimes one name maps to multiple addresses that change over time. And then there's some where it's a valid name, but it doesn't have an IP address. It doesn't have a host associated with it. Question?
So how is this IP address given to a server? For example, let's say I create my own server. How is that number generated?
Oh, how do you get your own IP address? Well, you have to beg, borrow, or you have to either borrow them or buy them. So, for example, at CMU, there's some number of what they call statically allocated IP addresses, where it's just fixed, assigned to that machine, and you can register for them and request them through computing services. But most of you don't have that. Most of you get one that's assigned dynamically. So there's a pool of addresses that you basically, they call them leasing, that you are assigned with for a while, and then, but it could possibly be reassigned to someone else. And that's part of the way it can manage a somewhat limited set of IP addresses. So the idea of like I said, the main way we'll think about it is in terms of what's called TCP. And it's this connection-oriented protocol where I establish a connection from one host establishes a connection to another host, and they can communicate to each other, sending arbitrarily long streams of bytes to each other. And so the connection is then two hosts that can talk to each other, and each of those endpoints is referred to as a socket. And so I can, and a socket is both an IP address and what's called a port number. So there's a 16-bit number for every connection that's referred to as its port. And the reason for that is just because I'm talking to a particular machine, that machine can support different services. It can provide SSH connections. It can provide FTP connections. It can host a mail server. It can host a web server. So a particular machine might have a multitude of different services. And so those are differentiated from each other with what are called port numbers. And similarly, I as a client might have connections to dozens of hosts going at any given time. I'm cruising the web. I'm doing all that different stuff. And that's all differentiated at the client end, that there's different ports associated with your different programs that are running. And so a port then is a 16-bit integer that identifies which particular endpoint is being communicated with at either the client side or the server side. And typically at the client side, these are assigned dynamically, and they're referred to as ephemeral ports, meaning they only are assigned for the limited duration that you have a connection with that, that you're maintaining that connection. And then there has to be some way, if I'm going to contact, and I want to know, the DNS will tell me what the IP address is of, say, google.com, but I have to know that, am I communicating with its web service, which is port 80, or HTTPS, a secure socket is a different port number. So which service I'm asking for. And there's a standard list, what are called well-known ports, that are that I can contact at the server end to get the particular service I'm looking for. And those are assigned. There's a big list of port assignments. And so, again, that's part of the sort of whole set of internet standards is the identifiers for the different ports, what services those are, and how those particular protocols work. So when I have a connection then, as I mentioned, think of it as a connection then as a link between two machines based on some known port, typically at the server end, and a dynamically assigned or ephemeral port assigned at the client end. And I can refer to then that connection then is identified by the combination of the hosts at the two ends and the ports that they're using. And in general, then, it's the job of the kernel to differentiate the different connections that are coming into a machine and figure out which software, which process to wake up when data, when some data arrives from another machine, and which actual program running on that machine will make use of that data. And that's done by associating for each of the ports a particular process executing program that's going to handle those particular requests. And it's totally possible for a client to be interacting with a single server over different ports. But those are considered to be different connections, and so they don't really interfere with each other. So that's what I mentioned is this is what we refer to as sockets programming, or the sockets interface. And it was developed sort of as the internet was evolving in the late 70s and early 80s. So socket then, as I said, is sort of logically one of the two ends of a connection. And from an application point of view, you'll see it as a file descriptor, just the low-level file stuff that you've already seen that you can do reading and writing from. And so that's a sort of mental model that is provided by the socket interface. But it's a very different, the actual implementation of network. When you write to a socket, it's firing up all kinds of network stuff, whereas you write to a disk, it's operating a disk controller. So at the hardware level and even at the lower levels of software, they're very different beasts. But you as an application programmer see some commonality there. Okay, so let's jump right into the API. And again, this is a place where you'll wish you were programming in a language that had type hierarchy, but you aren't. You're programming in C. So there's a type, there's a zillion structs that you kind of have to get familiar with, but one's called a sock adder. And basically, it's just a 16 bytes worth of stuff, where the only thing that's special here is that the leading 2 bytes designate what type of socket this is. In particular, it would be different whether it's a TCP socket, an IPv6 socket, a UDP socket, and all those will have different numbers, a different constant in there that tells you which type of socket it is. And then at the high level, the sockets, a lot of the programs don't need to know, which type of connection this is. They can just deal with, they basically call other software to deal with that. So that's why it's referred to as being family specific. And then the socket stuff isn't even necessarily referred to the internet, the capital I internet. And so there's a more specific one called a sockadder_in that is used for IPv4 sockets, not IPv6. And so in particular, it fills in fields. One is called the port, which, as I mentioned, is 16 bits. And then the IP address, the 4-byte IP address, both of which are in, even if you're running this software on a x86 machine, these should be in big endian order. And you'll see that this is what I mean, that this is sort of a C's version of subtyping, if you know something like C++ or Java or you know, a language with type inheritance. That you can think of it as a sock adder in is sort of a subclass of a sock adder, right? It has more information, it's compatible with, but has more information than a sock adder. And then there's another type of for IPv6 has a different kind of struct that they fill in for its information. And then they pad it out with 8 bytes of zeros, just because this particular protocol doesn't require the full 16 bytes. Okay, so this is sort of what it looks like to operate a full-blown client-server system from a programmer's perspective. And we're going to, for the rest of today and all of Thursday, go through all these steps. And you, as a programmer, are actually going to have to understand each of these steps, what they do, what they mean, and how to use them. The good news is there's some pretty standard patterns here, and so you can often grab some existing code, say out of the book, to use that will make this not as painful as it might look. So, but the overall idea of this picture then is, sorry, I can't get used to the fact my remote doesn't work. On the right-hand side refers to the steps that the server has to go through, and the left-hand side is what the client does. So the upper right is what it takes to set up a server that is then a program that's running there, ready to receive connections from a client and perform various services. And so obviously before the client can do anything, the server has to exist. So that has to be the first step in setting things up. And then we'll fire up a client that will make use of this service. And then there'll be what's referred to as a session, meaning a kind of back and forth communication between the client and server doing whatever they're going to do. This is not specific to any particular application. And like I said, it will involve, you'll see Rio underscore. Remember, those were our reliable I/O functions that we talked about as part of the Unix I/O. So it's a way to read and write and handle some of the quirks of low-level I/O, but basically this is sending and receiving messages over the internet. And then once that's done, typically then the client will close its connection, sort of the equivalent of hanging up its phone, and say, okay, I'm done. And then sometime later, or maybe never, depending on what kind of web service this is, if the server wants to shut down, it has its own collection of calls that it makes to stop that service. So anyways, just to kind of give you the landscape of what this picture means. So we're going to sort of jump into the middle, the top level, and we'll focus. Actually, which will we focus on? Well, we'll talk to some level in parallel, because there's a lot of commonality, as you can see, between what goes on with the server and what goes on with the client. And so actually the top level call, this one called getAdderInfo, is the way that it sort of initiates things and actually does the lookup to map from a domain name to a IP address. So we'll cover that later. So the first step on either side then in creating a connection is a call to a function called socket. And the reason I wanted a blackboard was to help you keep track of this. So the first call doesn't do much, and that's why the function call is socket, but it only happens within the application. It doesn't make use of any part of the operating system, doesn't send anything over the network. And the idea is to basically say, hey, I want to create a socket. It's given 3 arguments, the first of which is AF_INET. All these uppercase names are constants that are built in, they're included in the various .h files that you include in writing this code. And AF_INET just means it's a IPv4, so 32-bit addresses. And then the second parameter says you want a sock stream, and that refers to a TCP connection. It's referred to as a stream connection because, like I said, you get to send as many bytes as you like, a stream of bytes in either direction. And then 0 protocol. Well, I guess it must not be very interesting because I set it to 0. So we don't need to do anything in this particular case. There are man pages on this, by the way, which if you just tried to learn all of sockets programming by reading man pages, you'd go crazy. But once you kind of have the idea of it, the man pages are pretty useful. And then the next part, you'll see we're looking only now on the server side, is called bind. And what bind does then is that's specific then to a server. And now this is this interfaces to the kernel. It says, I want to designate which IP address. And let me just, sorry, I'm going to cheat a little bit by making sure I don't say anything that's not true. Yeah, I'm right. Sorry. I just wanted to make sure. Bind actually tells you, excuse me. You'll see that socket, the call to socket returns an int, but what it's returning is a file descriptor. Remember, we said that if you refer to a file, a low-level file, just by an integer ID, typically a small integer value. There's some standard ones for standard in, standard out, standard error, and then beyond that, they're just assigned incrementally. So socket will return a number that you then use to refer to this as a file. So bind, then you pass in the name of your socket file descriptor, and you provide whether these socket adder ins. And SA, I'm using the notation SA as a shortcut for sock adder, struct sock adder. And then you have to also say what the length of the address is. So in the case of IPv4, that would be 4. But you don't usually use that number directly. There's we'll talk about it, but that top-level call called getAdderInfo is a relatively new API that was created and is in this edition of the book, but not in previous ones, is become now the standard way that you get all the parameters that you're supposed to pass into all these different calls. And the idea of it then is it's a pretty small adjustment to then write code that's good for either IPv4 or IPv6. So you don't normally give the actual number from that. You get it from another place and pass it in. So binding then it's a kernel call. That designates which particular service this program is going to be hosting, or which it will be the server for, and that's given by its port number. And then the next step is to listen, and that's just a call that says, that will now convert this socket to a listening socket, which you need as a server. So it's a way of telling the kernel that this will be a server socket. So obviously, bind and listen are related ideas, but you have to do both steps, and in that particular order, to create a listening socket, or one for a server. And then the final part of that to operate is to say accept. And that means, okay, now we've established this. Now I'm actually ready to receive phone calls, is essentially what it's saying. This is the final step to say, okay, this one's ready to accept connection requests. And it has a similar set of arguments to socket, but slight difference. And now the interesting thing is accept will return yet another file descriptor. So the first file descriptor is the sort of generic accept, and basically accept will just hang there and wait until some client makes a connection. And when it does, then it will set up a new socket and with a new file descriptor that then the server communicates to the client via that one. And I'll talk about why it's a different file descriptor in just a second. Okay, over on the client side goes through similar steps of socket, but it doesn't have to bind or listen or accept because this is a client. And instead what it does is it makes a call to connect. So let me finish this off. So these are all on the server side. And on the client side, it will make a call to connect. And that's its job of that is from a client side is to set up a connection to a server. And so its arguments, it's a little easier to understand how Connect works. So in particular, the call to socket that was made beforehand returns a file descriptor. And what this says is I want to, on that particular, using that particular socket, connect to, this gives a combination of an address and a port number, and it has to give this address length, which I said, like I said as before, it's usually that number is filled in using the return value of getAddrInfo. But that's sort of the equivalent of placing the call then. And it returns just a code, which is whether the connection was successful or not. So let me just talk about these different ports and what it all means when you set up a connection. So when the server went through bind and listen, it created a listening port from that, which is the one that it's listening for connection requests on. And then the client, when it called socket, it was given a particular file descriptor for that, that socket. And it sends out a connection request that goes out over the network and lands at the server, and then the kernel hands that off to the program that's running on that particular port, and hands it off to that call will be handled by the accept, call to accept by the server. And then, as I mentioned, accept actually returns a new file descriptor, which the server will then use as its connection point to this particular client. And the theory of that is you want to be able to, in general, as a server, be handling multiple clients at the same time. Right? If I'm communicating with Google or Amazon, you should be able to do so at the same time. So you want the possibility of, from a single host, to be able to serve multiple clients. And that's why they're all assigned different file descriptors at the server end for that particular connection. So you can think of it as the listening file descriptor is just listening for incoming requests for connections. But once it sets up a session and communicates back and forth, those are going through different ports on the server side of things. Or different file descriptors, I'm sorry. Same port, different file descriptors from the software that's running on the server. Okay, and then during the actual communication then, as I mentioned, it uses reads and writes as a way to send and receive messages. And that goes on for as long as, and according to whatever low-level particular protocol is being supported by this application. And then in the end then, when the client is done, it closes the request. And what that looks like from the server end is it tries to read from a file and it receives an end-of-file signal instead. And that tells the server, okay, this particular connection is gone. And so now it will close that particular one. And as this picture shows here, potentially the server could loop back around and accept a connection from another program. And in fact, this can be done, this is what we call a serial or an iterative, a serial server where it can only manage one connection request at a time. And when we get later in the course and we talk about multi-threading, we'll be able to set it up so this thing can start accepting requests for another connection even while it's handling one particular client. But anyways, what it will look like is the server will read attempt to read, it will get an end of file, it will close that particular connection, and it will go back and it will accept a new connection from a new client. Okay, I'm going to jump ahead and actually start talking about some slides from that were, if you look online, they're actually from Thursday's lecture, because there's a lot of ground to cover in that lecture, and I'd like to get a little head start. So I mentioned this function called getAddrInfo, which is sort of the modern way, in C at least, to find information about that deals with all the funkiness of host names, host addresses, all the conventions about ports, and some of these various structures and things like that. And the advantage of doing it this way instead of the old way is, first of all, now it sort of unifies that IPv4 and IPv6 have very similar looking interfaces. And it's fairly easy to write code that can handle either. And the other was there was problems with these old ones that they were designed in an era before multi-threading. And so they have various statically allocated buffers, which gave a lot of bad conditions that you had to watch out for in writing code, and were prone to errors of various sorts. And so this new format, it's actually harder to use in many levels because it can't hide away as many details as it used to, but it has the advantage it works better in a multi-threaded environment. The other thing that makes it hard is it's trying to be sort of the kitchen sink of protocol managers, and that makes it a little bit nasty and messy. And so we're only going to sort of focus in on the parts that we really need to make use of for this course. So in particular, there's this function called getAttr_info, where the information you're passing is a host, which can be either it's a string, as it shows. Most of these are char stars, are actual real strings, not fake strings. It used to be, back in the old days, you use char star as a generic pointer because there weren't void stars. But these are actual strings. So you give the name, like the domain name of a host, or you can give the dotted decimal name, but written as a sequence of characters, 1, 2, 8, dot, so forth. A service, for example, that this is IPv4 TCP service. Some other information that's associated with this particular connection they refer to as hints, because again, this is trying to be a very generic looking call. And then you pass in a pointer, and it will fill in and return back a pointer to a data structure, which is essentially the way it's returning results back to you. And then associated with that is a call called freeAttr_info that will then deallocate the space that's used by this data structure from the result. And then there's one called getAttr_info string error, which lets you interpret the various error codes that get created by this routine, the value that it returns. So let's just look a little about this. And so the result that's returned by getAttr_info is a linked list that is null terminated, just like most linked lists are, where it gives some combination of the name of this particular some naming information for the first top level one is what I showed you, the canonical name for this particular IP address. And then it gives some address information, which is an IPv4 then that will encode the IP address. And it has a next pointer to chain this linked list together. And so this is actually one interesting thing about this is it sort of takes care of that many-to-many mapping, potentially, of names. So if I give, for example, google.com, it will return a linked list of all however many, or you saw with Twitter, it was returning about 4 different addresses. So this will return actually 5 list entries. The first will be the canonical name, and then it will give each of the 4 IP addresses that's relevant at this particular time. And then you as a programmer then sort of walk this list. You step down this list and typically try to use each address one after the other. And if you fail on one, then you try the next and try the next until you hit the end of the list, and then you say, oops, can't do it. And that goes whether you're writing a client or a server. So that Attr_info, let's look back at what that is. Oh, so Attr_info then is what gets returned is a list of Attr_info structs. And so the Attr_info struct contains various fields, which talks about what type of data is here. What type of socket is it? What its canonical name is. How long are its addresses? You saw that it's an argument to some of the calls. A pointer to a sock adder struct. That's the way that is encoded for IPv. What we've already seen, sock adders is a sort of low-level data structure that gets used. And then a next pointer to chain the linked list together. And so you'll see some of these are the arguments that then you will use to pass into the other functions like bind and listen and connect. And then there's another version called getNameInfo, which you use when you've got an IP address and you want to find what is its domain name. And because you remember that mapping is also potentially a one-to-many. There can be multiple domain names associated with it. And so it has a similar general thing. We'll just look right now at getAddrInfo. So just as an example of how you'd write code to make use of this, and essentially just as a way of probing the DNS server, is I want to set up an argument, a call to getAddrInfo, where the string I'm going to pass the name is whatever I type in at the to this application, to main. And it just for hints just passes a bunch of zeros. And list P, again, this will just be a pointers that I haven't actually oh, okay. So you'll notice hints is actually a struct itself, whereas list P and star P are just, list P and P are just pointers to structs. They don't have any allocated data. So the hints, I'm just going to fill in that struct with all zeros, because I don't really need to provide any hints. I am telling it that I want an IPv6 TCP connection here. And then, so what it will do is it will return back, well, it returns an error code, but it will return to me a pointer to this linked list data structure I showed before. And now I can step through that list using standard linked list code and make calls to the getNameInfo function, which will return back domain names. And then when it's all done, I have to free up that list that got returned. Otherwise, I'll create memory stuff. So just as a demo, where am I? Oh, host info, sorry. So you can think of it, this is like a not very fancy implementation of NSLOOKUP. So the kind of stuff we already saw before, but let's all it's returning are the different addresses. And one of the things that I found curious is it returns them in the same order all the time. Instead of with NSLOOKUP, it kept changing it. And I think that has to do with caching. No, that changed. I don't know. It's kind of interesting. You might want to play with this code. It's kind of, you can see what's going on in different places. And so you can see, though, that it's basically getting the same kind of information that you would from NSLOOKUP. It's really just querying the DNS server to do this. But that's the start of what some of this code looks like. And One of the things, by the way, when you're writing your own code, you often make use of what's called localhost, and that always just refers to the machine that you're running on, and it always has this particular IP address. So that address just refers to the machine, and as a programmer, you do all your testing on one machine. You just set up both the client and the server on the same machine and play with it. So localhost is a very useful way of doing code development. And as this shows, you can request host info for other things given. And you can also, by the way, always give a dotted decimal address. And I'm just making it up here. And it's not very interesting because it returns back the same address. It's more interesting to run NSLOOKUP on that. So that just gives you a sense. And as you've seen, this code is pretty messy stuff to work with. There's a lot of structs. You have to initialize. You don't initialize. You pass pointers. And so the code always looks a bit crufty, but that's sort of the interface as it exists, and you'll just have to get somewhat comfortable with it. So that will do us for today then. Thanks.